So the first thing I want to do is review. Yesterday we covered a lot. Last time we covered quite a lot, and it's difficult material. So I want to go over that ground to remind you of where we got to, and today we'll spend a good piece of today just going over that ground again and reminding you about what it means. We're live, but we're shaking because the camera is flying through the air. Okay. Anyway, so we started with this problem, regression. And regression stated as a problem says, I've got these regressors, one per data point of each regressor. So they're these big long vectors that are as long as the number of data points you collected. We gather them up and stick them in a matrix called X. We'd like to take a weighted combination of them and get as close to the Y's as we can. So that weighted combination has weights beta, one per regressor. So we would like, for every data point, which is in the X's, one per regressor. Let's imagine that it's two regressors, because all these pictures will be for two regressors. So we've got two regressors. So for every data point, I've got an X, a first regressor and the second regressor value. And then I have the dependent variable, the Y. And I like to have a weighted combination of these come close to that. And I'm going to repeat that for every data point. And square them and add them up and call them the error. So this is the error. I could put a square on that, by the way. We talked about squared error. But minimizing squared error and minimizing length are the same thing. But just to be consistent, I'll put the little 2 there. We're going to use it later anyway. Okay? So that was the setup of the problem. So we went through the principle of orthogonality, which is once you account for it, the vector of the errors should be perpendicular to all the regressors. We went through a big, long proof to come up with an answer. We did it 2 different ways, a geometric way, an SVD way. We came up with 2 different answers, one of which ended up being the pseudo-inverse of x multiplied by the y's, and one of which ended up being this funky-looking formula. And then I spent a good long time proving to you that these were identical to each other, which they should be since they're both solving the same problem. Okay? So that's just a summary. It's just symbol pushing based on the geometry that gets you directly to the answer, closed form answer. So having the error measured by quadratic error, length squared, allowed us to get a closed form answer. And that's why people often like to use squared error, because it's often the easiest problem to solve. Okay, and looking at the first answer, it says, oh, I'd like to move x to the other side. So if I wanted y equal to x times beta, if I could invert x, then I'd be done. You can't invert x, because in general, x isn't even square, right? You've got 2 regressors, but 2,000 data points. So it's a 2,000 by 2. You can't invert those. But you can invert them as best you can, and the definition of invert as best you can is the pseudo-inverse. Invert what you can, give up on the rest. And the pseudo-inverse leads to the fact that you cannot fit y perfectly. You fit it as well as you can. So the next thing that we talked about was, what do the mistakes look like as a function of beta? So this is the closed form of the best beta, and it doesn't fit it perfectly. And what happens if you use a beta other than the best beta? So one thing I went through, and I'll admit I went through it, with ugly drawings and done rather quickly, was trying to interpret for you what the error looks like. So I went back to the proof of how we got this formula in the first place. And the way we did that when we did it with the SVD, so we got this formula, not this one. We got this formula, we used the SVD. And the way I got there was to start with the original problem, which had y and beta as the 2 vectors we were playing with, and x expressed as an SVD, as US V transpose. Okay, I took that and then I moved some symbols around. And the first thing I did is I rotated, I moved the u and v around in the formula for this. I'm not going to reiterate everything I drew, but just in broad strokes, that's what I did. And I did a change of variables. I replaced y by a rotated y, rotated by u transpose, and I gave it a new name. I rotated beta by v transpose, and I gave it a new name. Okay? So in the beta space, all I did was a rotation. Then I had a formula that had s times beta star. And so I absorbed the little s's into beta star. So I multiplied the first beta by s1, the second beta by s2, and if there were more, I would do those. So now what I've done is I've stretched the axes in beta space. And that left me with a formula over here in another change of variables. Y star didn't change, but beta went to beta double star when I stretched it. And over in this space, the formula looked incredibly simple. I wanted to minimize y star. Oh, did I draw this somewhere? Yeah, I drew it here. I wanted to minimize this formula. Now I've got the y star in quotes now. What I actually had was a funny S-shaped matrix that had singular values that were ones, because I took the s's and absorbed it into beta star. So I'm not going to go colloquial on you. I had this y stars and these beta double stars. Now the y star is a big long vector, right? I collected 1,000 data points, 1,000 numbers. But I've now rotated and stretched and gotten into this new space where the first ones, for example, if we're only in 2 betas, where the first 2 I can fix completely. I just set the first one of these to look like the first one of these, and the second one of these to look like the second one of these, and so the first 2 data points worth of errors are now 0. And the way this all worked, everything below there I couldn't fix. It was where the S matrix is all zeros. I can't fix it at all. That was the irreducible error. Okay? So that was my solution. Now in this space, I've got the irreducible error, all the y's below where the s is all zeros. And then I've got this, where the solution is to set the betas equal to the first elements of y star. But if I used a different beta, not the optimal one that kills the early error, but one that's off, I'd say what would the error look like as a function of beta? So at some beta, beta opt, right here, this is beta double star opt. That's the best one, which is equal to y, the first few y's. At beta opt, the error is non-zero. I didn't actually put that on the board, and someone asked me afterwards about it because it confused them. My bad. There's irreducible error. So, for example, we killed the error for y1 star and y2 star. We set it to 0 by setting that appropriately at beta double star opt. But all the rest of them, y3 star, y4 star, down to y1000 star, we aren't fixing them at all. So the sum of the squared of those numbers is error that's always with us. It's the length of this lift off the coordinate plane. Okay? As beta goes away from beta opt, the value of error that it increases by is this difference squared, which is like a length of a vector that goes from beta star opt to the beta star. Beta star opt is what y star is at the top, the first 2. And so when we go away from there, we're saying, as I go away from this point in any direction, the error is going to go up by this length squared. Otherwise known as we're going to get a problem. And that the regions of equal error are circles around beta opt, circles in the plane. You go up and they'll have equal error. So these are meant to be circles viewed from your viewpoint. Okay? So it's just a paraboloid. The circles get bigger and bigger. That's what the error looks like in this space. But we'll want to know what the error looks like back in beta space where we started, which means I have to take these 2 things that we did and we have to undo them. So how do we undo them? Well, this was stretch the 2 axes by the singular values. So going back this way is shrink them by the singular values. And if you take a circle and take one axis of it and stretch it or shrink it, what you get is an ellipse. It's kind of the definition of ellipse, right? I'll go to the wrong board. X squared plus y squared equals 1 is a circle, and x over a squared plus y over b squared equals 1 is ellipse, where you've stretched this one by a and stretched this one by b. Okay? It's just a definition of this ellipse, but a specific ellipse that's aligned with the coordinate axes, because you stretched the coordinate axes, which means when you go back here, you get ellipses instead of circles. and they are aligned with beta 1 star and beta 2 star. And then when you go back here, we're taking beta space and rotating it by V going back. It's just a rotation, which means we're going to take that set of parabolic, I don't even know what that shape's called, elliptical paraboloid? That might be right, I have no idea. But that thing, we're just going to rotate it. So it's still going to be an elliptical paraboloid, it just won't be aligned with the axes anymore, which is what this horrible drawing is meant to represent. Okay? It is still, above the plane, because that irreducible error isn't changed by any of this. Okay, so it's still lifted above the plane by an amount which is y3 star squared plus y4 star squared plus y5 star squared, 1 is y1000 star squared. That is this length. And then it gets bigger as you go away from the optimal. The bottom here is beta opt. The bottom here, I don't know where it is, let's say it's there, is beta star opt. Okay, so that's where it's best. And as you go away from that, you have a squared error, so it's going to look like something like a quadratic. And in 2 dimensions, a quadratic looks like an elliptical paraboloid facing some way or other. Okay, that's stuff we said last time. We then went through this notion about what happens if you use some other thing other than quadratic error. Because we did the quadratic error version, and quadratic error is very pleasant. It's nicely behaved. Often you can get closed form solutions. We then talked about convex. Convex being the error as a function of as you go away. So in 1 dimensions, if this is error, and this is how far away you were from the optimal. So we were using a quadratic error. Y equals x squared. But you could use any number of other things. You could use y, some other power other than 2. You could use this, which is absolute value of x cubed. You could use something shallower, absolute value of x to the 3 halves. You could use what's called L1. You could have it be a straight line, which is to say absolute value of x. So these are all kind of distance metrics about how far you are away from the right place. They're district metrics which often have a name. They're called norms, meaning they're like a length, and they satisfy the axioms of length. So L1 would be the straight line norm. This guy would be L2. This is L3. This is L3 halves, etc. You could use any one of those. And all those so far are convex, as named by me so far. Why? Because for any one of these curves, if I take 2 points on them and I connect it with a straight line, that straight line is on the curve or above. For L1, that straight line is actually on the curve. It doesn't even get above it. But for all of those, you have this nice feature that if you don't know where the right place is, if you guess, and guess a place, say over here, I think this is the right answer, you can measure the derivative of this thing and say, oh, downhill's that way. And so I'll just allow this guy to roll downhill. And when it gets to the bottom, I'm guaranteed to be in the right place. So that's what we mean by iterative descent. Just head downhill, and you might go too far, right? I mean, if I roll down here, but if my next step is over here, my error will increase. So say, oh, I went too far, let's go back, less far. But either way, I can go over and over and over again, taking steps in the downhill direction, taking smaller steps eventually, and eventually I will be guaranteed to converge on the right answer. And this is not just true in 1 dimension, it's true in n dimensions. Now in n dimensions you have to decide what downhill is, so go back to multivariate calculus if you ever took it. So the thing you're doing is not just one derivative, it's derivatives in all the coordinate directions, otherwise known as the gradient, which points downhill. Okay? So it points up on the negative gradient. So that again doesn't give you a closed form solution that you can get to the answer instantly, but it gives you a computational algorithm that will get you where you want to go. And I quickly went through the notion that if it's smooth but it's not convex, so if you have an error metric which is convex up for a while and then it's concave down, we're going to talk about one of those in a while. But if it starts becoming concave, you may end up having an error function as a function of the guy you're working with. So I'm going to erase some of this now. So we're just going to take beta, one of the betas, beta 1 say, an error. And if this thing stops being convex, it might do something like this. Which means you'd like to get here, but if I drop a marble from here, I'll end up at the wrong spot. So gradient descent is not guaranteed to get you where you want to go. So what do you do about that? Simplest thing, you do a grid search to start, meaning you pick a lot of places and you try them all. And if you have a really fine grid, you know, hopefully you won't miss it. Of course, if the error surface looks like you do a grid, you might miss it because it might be such a narrow little valley you may not see it. You don't know how wide the valley is. So none of these things are guaranteed to work. You can start from lots of starting points and then roll downhill from those starting points and, you know, pick the best one. And most of the time you'll do okay, but it can fail. And this idea of doing a fine grid is perfectly fine if you're doing a one-dimensional search. So if your problem only has one beta, then fine, do 1,000 values. It won't take very long. But if you have 2 betas and you want to be as good about it, then you have 1,000 times 1,000. Now all of a sudden you have to call the thing 1,000,000 times. 3 betas, you're now up to 1 trillion. Okay? 1 billion, sorry, whatever. The point is, it doesn't behave as the dimensionality goes up, which makes it really hard. So you can take a whole semester course in thinking about how do you solve these problems of finding global minima or trying to find global minima for difficult problems. And as you saw, if it's not even smooth, you know, you're shit out of luck. That's the technical term. Okay. So now let's go back to the meaning of what we did. So we just went through how do you fit a straight line or a plane or whatever to a bunch of data, multivariate, we can't put the solutions that I just wrote down. And, you know, if it's a one-dimensional fit and, you know, these were your x's and these were your y's and it looked like this, I mean, if you could plot it and look at it, you'd say, yeah, that's a reasonable fit. And it's probably the best I could do. And you'd be happy with it. If you plotted it and it looked like this, you might say that, well, fine, it may be the best fitting line, but a line doesn't explain these data and something else would explain them better. And there may be some set of functions that you might want to fit to find a function that fits the data well, because it looks like here, you know, you're doing something silly. You're fitting a straight line to something where a straight line doesn't fit. And in particular, for that second example, so you fit this line, but the data look like this. If you took the mistakes, this mistake, this mistake, this mistake, and you plotted the mistakes as a function of x, you would see that the mistakes, you know, look like this. They don't look like noise, they look like a function. Okay? The mistakes in this case would be, oh, here's a negative mistake, here's a positive mistake, here's a negative mistake, here's a positive mistake, here's a good fit, here's a positive mistake. It would look like just kind of random noise. You want the residuals, these are the leftover errors, or sometimes called the residuals, especially in a statistics framework. You want the residuals to be unpatterned. You want them not to show a pattern. If they show a pattern, that means there's something about the data that you missed. Okay? So in the second example, you might want to fit some kind of function other than a straight line. And in just a second, I'm going to talk about how you might do that. In the third example here, this is going to get at some issues about the error function that we use. In this third example, it looks like there's a perfectly good straight line, and this guy should get remeasured. You know, somebody copied the numbers down wrong, or somebody's equipment failed, or something. This guy's called an outlier, and you might want to do something to fix it. We're going to talk about that today as well. Okay? Now, why is the line pulled up as much as it is? Just when there's only one data point that's wrong. What is it about our procedure that caused that data point to have huge influence? on the resulting fit, even though it's only one single data point? It's because the error is squared. And so if you go twice as far away, you're contributing 4 times as much to the error. You go 6 times away, you're contributing 36 times as much to the error. And so you've got enormous pull on that line as a single data point. Yeah?
So by the same regression fit here, do you mean they have the same error?
Say that again?
It says that these 4 data sets have the same regression fit.
The blue line is the same in all of them.
Okay. Gotcha.
Yeah. Not the same error, but the same fit. So outliers are concerned, and they're detectable. There's ways you can decide, oh, this guy looks like he's an error, maybe I should do something about him and give him less weight, which will lead to the idea of having not all points contribute equally to a fit, which is another thing that we're going to do today. So I'm sort of using this graph as an outline for what we're going to get to. And over here, well, this is just a silly data set, right? Most of these data points are doing absolutely nothing, and you're effectively fitting a line to 2 points. One, the mean of these guys, and one, this other guy. And of course, you can fit it exactly. You can't fit these guys exactly. But that's a little silly. Okay, now before we get to that, let's think about how constrained is this fit. So we've been talking about fitting a line. So suppose I ask, when is this fit going to fail? So when is the fit ambiguous? So the fit was non-ambiguous because the error was this parabola, which means there was a bottom. And that parabola could be flatter, could be steeper, depending on the kinds of errors. But when does the error go completely flat so that you are ambiguous as to where the line should go? You have no idea which line is best. You have no idea which beta is best. What could I do with a set of data points that I could put right here such that it would not matter which line I picked? So we're going to do a 1D problem. It could be this line, this line, this line, this line, this line. Where would the data set have to be such that the line was completely unconstrained? Origin. Okay, I only have one data point and it's right there. This fits perfectly, this fits perfectly, this fits perfectly. That's not the only example, that's an example. Okay? How many data points have I put at the origin? I didn't tell you. That could be 1 data point, that could be 50. Okay? Still a problem. Can I put some data points off the origin and still have the same problem? There's an almost example on the screen.
So pick one to circle.
We'll get to that one in a second. That's a interesting idea, but it turns out it doesn't fix this problem. So if I add another data point here, or another data point here, another data point here, the line has to go through the origin. Those errors through the origin can't be fixed, and so I'm completely unconstrained. That means that the error function as a function of beta has gone flat. Now, Marissa suggested the following idea, which in fact is in the video for this course about 2 years ago, which is to do this. And no, Arrow, I won't go over what happened in that class. Which looks symmetric. As far as regression is concerned, I'm saying that's symmetric. I'm sure why Marissa came up with this idea. Okay? But what happens when I go from this line to, say, this line? So on the so as I go from this line to this line, these errors just got reduced, and these errors got increased. Do they cancel?
Square.
It's squared error. They don't cancel. Linear regression for a case like this gives you a horizontal line through the origin. For uncorrelated, and we haven't talked about correlation in this course yet, we will eventually, but for uncorrelated data, the solution is a flat line. However, suppose we weren't using L2. Is there a standard convex norm of the sorts that I talked about just a minute ago, for which this would, in fact, be ambiguous. For which, when I put the line up, some errors get smaller, other errors get bigger, and they cancel out, so that the total error doesn't change at all. Which norm would, in fact, find this an ambiguous stimulus, an ambiguous data set? So beta would be unconstrained completely.
But you have a single dot at the right extreme, right?
What's that?
I mean, you have a, so on the x-axis, you have two dots that don't have a pair.
Okay, let's go to another data set, because now I'm realizing that this is not the example we used for the question I'm now asking you. So let's go to this data set, which is the one I meant. You're right. This one, I think, will in fact change with all the L metrics, but I have to think about that a little harder. Let's think about this data set on the right. So this data set on the right has a left-right symmetry, right? And if I choose this one, so first of all, let's think about the L2 norm. So I could choose the flat line, I could choose this line, I could choose this line, or some others. So if I choose this line, I account for this perfectly, and suppose this is at +1, my line's at -1, the error is 2, the total error is 4. Okay? I can use this line. Perfect, perfect, -1 or +1, error is 2, squared error is 4. If I pick the flat line, this error is 1, this error is 1, sum of squared errors is 2. So the flat line works better. Okay? And in fact works best. But suppose instead of using squared error, I use some other norm. Is there a norm such that all three of those lines give you exactly the same error? Instead of L2, I want to use L something else. Not error squared, but some other function of the error. So what function of the error would be such that if I decrease one and increase the other by the same amount, they would cancel? Answer, don't square them. Use L1. This line has an error of 2. This line has an error of 1 + 1 is 2. This line has an error of 2. They all have errors of 2. If you overdo it, and you go up here, remember there's an absolute value sign in the L1 metric. They stop canceling. Okay? But as long as you stick between +45 degrees and -45 degrees, they're all ambiguous. Okay? So the L1 is kind of special in that way. It can be unconstrained by symmetric data. All the other ones won't have that property. Okay, so that's just a little bit about thinking about the kinds of things this thing is trying to do. Now, let's start talking about how we answer some of these examples, in particular these two. Yeah?
How do you choose when to do L1 or L2 versus?
Every time you have a problem and you state it in terms of some function I want to minimize, sometimes we, call that a norm. Sometimes we call it a cost function. It's the cost of errors. So if there's a real-world cost of errors, that turns into money or something that you want to minimize, there might be an impetus for picking a particular one. For taking some arbitrary statistical problem, you're in fact, in some sense, doing something ad hoc until a problem hands you a metric. So some situations you may have a metric. So in some of the experiments I do in my lab, we're often putting humans in situations where they're doing a task and there's payoffs if they do well and penalties if they do poorly. And so I've monetized a task and they're actually trying to optimize a real thing. Some of the expected amount of money you're going to make in the hour as a subject in my experiment. So that one's given to you. But for these abstract problems, you either need a motivation for saying this metric's the appropriate one, and if you don't, what most of the field does is picks quadratic error because it's the one that's mathematically convenient. Not necessarily right, but it's mathematically convenient, so without having anything else to push you towards one. But they will behave differently for different data sets, and so it's really a question of which is the cost function that you meant to use because of how you were thinking about your problem. Thinking through examples is one way to do that. Think about what is it you really need, what is it you really want. Want is minimized costs, so that's a definition of cost. So there's no good clear answer. This specific problem, this is the right norm. It's really thinking about what is it you're trying to get your technique to optimize. Okay, so we're going to solve these two exemplars. And in particular, let's start with this one. This one says, maybe I don't want to fit a straight line. First of all, some of you may have been wondering why, through all this time, we were talking about fitting straight lines, but we were forcing ourselves to go through the origin. Right? So when we set up the problem of, y equals x times beta, we took our data points and they got stretched by beta, but they were never allowed to move up and down away from the origin. Okay? So you might want to fit a more general function, not just your regressors stretched out and summed together, but some other thing. So one way to think about this is to think about the 1D problem. So y is one-dimensional, x is one-dimensional. Okay? So we've got a bunch of data, and they're living in 1D, and and here's x, and here's y, and we've got a bunch of data points, which, wherever they are. Okay? I'm making them up, but they certainly don't look like a straight line. That was intentional. Okay? And you might want to, and they also look like the right curve probably doesn't go through the origin. So this is a one-dimensional problem, which if you're going to set it up as y, is approximately equal to beta times x, and beta doesn't have an arrow because it's the 1D problem, well, that's the 1D problem we solved in the very beginning of last time, line through the origin, and I gave you the solution to that. But suppose I'd like to say that y is approximately equal to beta 0 plus beta 1 x plus beta 2 x squared plus beta 3 x cubed. So I want to fit a function, but not necessarily a function through the origin. Well, we already know, so now all of a sudden I don't have 1 beta, I have 4 beta, so beta is now a vector. Okay? Which means the setup, again, is y is approximately equal to, so I'm going to take a little x, I'm going to replace them with a matrix that I'm going to describe in just a second, but x times beta. That's the multivariate regression problem. But what are the things I'm trying to fit it with? Well, I would like beta 0 to be the same for every single data point. Right? Which means that beta 0 is effectively multiplying by a regressor that doesn't depend on which data point you are. So I'm going to make regressors, which are big column vectors as many as my data points, and one of those regressors, which will multiply by beta 0, is going to be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. It's going to be the same for everybody. Beta 1 wants to multiply by the raw data. Well, we've done that before. That's easy. That's was beta 1 times x1 or x2 or x3, ... Beta 2 wants to account for the data as a quadratic. So plus beta 2, data is a quadratic. So now I've got to take x1 square them, x2 square them, ... In other words, if I want to fit a polynomial, I'm going to take my measured data and regress it against my independent variable, and here I'm acting like the x's are nicely ordered. They don't have to be. I'm acting like x1 happens to be 1 and x2 happens to be 2, or what? No, I'm actually acting like x1 is minus 0.4, and x15 is 0, and x30 is, whatever. I've picked a set of x's that are nicely arranged in the x-axis. So that's beta 1 multiplies by x, and beta 2 multiplies by these values squared, otherwise known as a parabola. If you want to fit a cubic, there'd be another regressor, which would be the x's cubed. Okay? And by best fitting that, you are best fitting a function of this form. So this silly vector that doesn't even use your x's, this vector of 1s, is the thing that lets you lift it away from the origin. Right? Because if you set beta 0 to something other than 0, it means when the x's are all 0, when you're at the origin, the value is not 0, the value is beta 0. So it lifts you off the origin by this much. and this one acts like straight line, this one acts like parabola, etc., etc. You can play this trick with polynomials, and for that curvy thing that I showed you, that exemplar where a straight line doesn't fit, it would put a whole bunch of weight on x squared in order to get it to curve. And if it's a perfect parabola like this, it'll put all the weight on x squared, but if it's effectively skewed off the origin so that the bottom of the parabola is not 0, it's some other value, then it's going to have to add some straight line to it. And so it'll, within the class of functions of a plus bx plus cx squared, it'll pick the one that best fits your data in the squared error sense. Okay? So that's fitting with a particular set of functions. And this is actually a general trick. You could fit with polynomials. You could fit with sine waves, coming up soon in a classroom near you. You could fit it with some other set of functions. Use step functions of various shapes. There's lots of ways to pick a class of functions and decide, how well can I use that class of functions to fit my data. Polynomial is just kind of a standard example, comes out of high school math, and certainly high school calculus, where you learned about approximating a function with a Taylor series. So that was one of the first things to do after derivatives, to say if I want to approximate this fancy function as a polynomial, calculus gives me what the betas should be. But if you have raw data, then you do fit. And when you do that, you have to be careful. And I'm just going to point out the problem now, but the solution to the problem will come actually a month hence. But here are some data, a bunch of red dots, and I can fit them with no regressors. Sorry, with one regressor, the constant function, that's beta 0. Then I can show in beta 1, so I can have a line, doesn't have to go through the origin, and it looks like it's not really accounting for the data very well. Then I can add an x squared term, and this is doing quite well. I can add an x cubed term, and I obviously will always do better. Why? Because the function I had before, the function I had before is already in there. I'm just adding one more degree of freedom, but the old degrees of freedom are still present. So every time you take another step to the right where you're adding a regressor, but including the regressors you had already used, you will always do better. Guaranteed. You cannot do worse. You may do the same, and you would do the same if beta 3 here was 0. But as soon as beta 3 is anything else, that means that you're using beta 3 to get closer to your data. And you get closer, and you get closer, and you'll get closer. And, how many data points did I have? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 degrees of freedom in my data. For every x, there's a y. So I've given you the 8 y's. That's all the freedom that my data has. And if you give me 8 betas, I fit it perfectly. I fit it perfectly, but look at that function. Does your data give you any indication whatsoever that if you're halfway between this and this guy, you have to go down to -50? There's nothing in the data that indicates that. So this is obviously, fitting your data, but it's fitting the noise in your data, not just the signal in your data. So this is referred to as overfitting. And we will talk about techniques, not today, but in future lectures, about how do you detect that you're overfitting, how do you prevent overfitting, how do you pick how many regressors is enough. And there are, in fact, techniques to do that, but the idea being, your data, maybe justify this, but they certainly don't justify this. You added a regressor and you fit this data better. Your squared error at 5 is better than your squared error at 4. You fit your data better. But now all of a sudden, your extrapolation to the left of your data goes down, even though the data are smoothly going up, but for some noise. Okay? And so the right answer is probably somewhere between 2 and 4. I don't know which, but it's somewhere there. Because this is obviously not justified by the data. And so, again, we'll talk about techniques later on about what is overfitting and how do you detect it and how do you decide how many regressors are enough. But the issue is here it's really easy to see that there's a problem. You just plot the data, you plot the curve, and you look at it. But when you have 1,000 data points in dimensional space, and you're fitting, beta 1, x1 squared, x5 squared, the fifth dimension, x1 times x5, you're fitting this polynomial that's got lots and lots of bells and whistles on it. You can't plot it. You can plot little, cuts through the data. You can plot 2 dimensions at a time, maybe 3, to try to look for these problems. But you need techniques that will indicate these problems to you without plotting them. So it gets hard once dimensionality gets big. For 1 dimension, you can just plot this and it'll be really obvious what you mean by too many regressors. So it's not as trivial a problem as it looks like here once your dimensionality of your data gets big. In any case, that's how you fit curves other than straight lines through the origin. Next problem, this guy. So this guy looks like a problem because there's a data point that looks untrustworthy. Now, a data point may look untrustworthy because you did a fit and it just looks like an outlier. But a data point may be known to be untrustworthy before you started. So imagine, for example, that you sent out samples of something to be measured by a whole bunch of labs, and you have lots of these samples, and you're getting all these data back. And you learn afterwards that there was an equipment failure or something in one of the labs. And so you could just not use those data, but maybe they have some value, but maybe you know how much noisier they are, and so you want to unweight them. So the next problem is the notion of weighted regression. I don't remember if I have a slide for that. Yes, I do. Good. So the idea being, we were trying to get the data, the dependent variables to look like something from the independent variables. And this is kind of the 1D case being written here. But you may have the notion that some data points are worth more than others, and so you're going to give them weights. And so you're going to have the error count more for a data point you trust, and count less for a data point that you don't trust. Okay? And so how do we solve that one, and how do we solve that one in the general case? So it turns out it's trivial, used based on the math we already know. So let's write it out in a multi-dimensional case, and then let's solve it. So the multi-dimensional case is as follows. Let me just not trip on myself. Take my cheat sheet with me. Okay, so we want, the case we used to have was y. The error is y minus x beta in the multi-p case. It used to be that we took that error and we took its squared value and we picked the beta that minimized it. That was the problem we solved last time. So now I want to weight these errors. I want to have a weight matrix that affects all these guys. So what's the form of W? So y minus x beta is error 1, error 2, up to error n. That's what that looks like. That's what this looks like. But now I want to weight each of these by different numbers. So I'm going to make a weight matrix, which is going to be n by n. This is going to be W. And I want to weight these different errors. So I want a weight 1, that's going to multiply by E1, and I want a weight 2, that's going to multiply by E2. In other words, I want the result of this to be W1, E1, W2, E2, Wn, En. Which is to say that the W matrix wants to be a diagonal where you put the weights on the diagonal. Okay? That's what we're going to do. So, W is just given to you by fiat in weighted least squares. We're going to talk later about particular weights we might want to use, but just suppose that you've decided that the first 10 data points came from the dodgy lab, and so we're going to give them half the weight. And so our matrix is going to be half, 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 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? So suppose that's just somehow given to us. Okay? So let's look at what we have here. multiply it out. Min over beta wy minus wx beta squared. Okay? So wy is just another vector. It just takes the first 10 data points and 10 independent points and multiplies them by half or whatever. Okay? So that's just a new vector. I hate to do this to you, but what the hell? Let's call it y star, which is just that, minus x star beta, where x star is just that. So you recognize that weighted least squares regression is just regression. It's the same problem. We know how to solve it. The solution is that y star equals, what am I saying? The solution is to take x star same solution we had before, except the guy we're inverting, pseudo-inverting, is not x, but it's wx. Right, and that's about all there is to it. Yeah, and so that'll give you your beta. Right. Yeah, so that it's the same thing. It's the same math. It's the same solution. Same everything. Now, note, the thing we're going to do to get the solution, the thing we'll take the SVD of, the thing that will, do all that stuff we did, will not be x, the matrix. It'll be wx. The SVD of x doesn't enter into this. It's wx, or x star, that you're going to use the SVD of, that you're going to do the pseudo-inverse of, etc. Okay, so it's just a transformal way of a problem where you treat some of the data points differently than the others, and where you also have to pay attention to the fact that the weights also apply to y when you do the inverse to get your optimal beta. That's it. Otherwise, it's the same math we already used. Okay, let me think about where I'm going right now. Yeah. Yo, question?
How do you get your weights?
How do you get, you mean betas? Oh, how do you get your weights? So as I said, if we are handed them, is that hot? If we're handed them, here's the math. But there are places where the weights come for a reason, and that's the subject of the second half of the class today. So I think this actually, it's 5 to 11, a good breaking point. So let's take 5 and reconvene at 11. We are live.
It's just the structure of the first one.
Yeah.
Are we having lab this Friday because of the P1?
No, there's no lab this week, right?
No lab.
Oh, is the schedule not up?
It is.
Okay.
There's no lab this week. I guess it's not obvious because it's just not there.
Yeah, there's no lab this week.
Okay.
Yeah. No, we try to avoid obvious conflicts, and having a third of you not be able to go is definitely a biggest conflict. Other questions before I? Okay. So we talked about outliers a bit ago. There was an example where everything seems to fit except that there's one data point that looks weird. Okay, and the question is, this, because of squared error, if you're using squared error, is going to pull a regression line pretty far away from where, at least visually, it seems like it belongs. It seems like you should be able to notice that you have an outlier and fix it. So one solution to this is to literally look at the errors of your data points from the current fit and just plot them. So that's what I'm doing here. I'm taking all the data points and saying how far are they away from the line. So going back to the line, I'm just taking these vertical distances and counting binning them and plotting how big they are. So these vertical distances could be, they could be below the line, they could be above the line, whatever, but that outlier is sitting out here all by him or herself, okay? Making it obvious that you have an outlier. And so one thing you could do is effectively delete the outlier. Just throw the data point away and start over again. So this is called trimming. And one way to do it is to literally shorten all your vectors and just delete that row. Okay? And so you just now have a new regression problem where you've just decided that's a bad data point, I'm not going to use it. Another way to solve that trimming is to use weighted least squares regression and give that errant data point a weight of 0. Same thing, right? You give it a weight of 0, by the time you're done with all turning the crank, you're going to get the same answer as if you just deleted the data point. Now, you could just do that once and say, I'm done. Or you could do it again. So I've got my data. This is the blue line I showed you before. I did a histogram of all the errors, and there was one error that was way bigger than the others. So I said, okay, I don't like that data point, let's throw it away, or give it a weight of 0. So then I refit, and now I get this red line, which certainly looks a lot better. The data, in fact, were generated from a true line, which is really close to the red line. But having gotten this new red line, having already deleted this data point, I can take the new errors from the red line, and try again. Plot a histogram, that little bar graph, of all the errors, and see if there are any data points left that are still way far away from the line compared to all the others. Because that red data point may be 10,000 times further away than everybody else, but when you refit again, there's still maybe one guy who's way bigger error than the others, which you still want to throw away. And so you could keep doing this over and over again. So this is called an iterative algorithm. It's called a greedy algorithm because each time you decide to throw somebody away, that guy's thrown away for good, and then you go look for more that you can throw away until you decide somehow when to stop. There is some ad hoc in here about when to stop. In other words, what constitutes a set of errors such that nobody is too far away. Later on this semester, we'll talk about standard measures of variance. And so you could compute the standard deviation of your data and say, okay, as long as none of the data points are more than 3 standard deviations away from the mean, then I'm fine, but if anybody's further out, then I'll trim them away. So you could come up with a recognizably ad hoc, but at least overt criterion for when do you stop, okay? And so that's one way to go. Now, the reason we did all this trimming, or this iterative trimming, or whatever algorithm we use to decide that this is a bad data point, oh yeah, this also is a bad data point, the rest of the data points I'm going to treat as good and they all count equally. Why did we have to do that in the first place? Why did we not want this data point that was way off the line? What was it doing wrong? What was the problem?
Skewing your fit.
It was skewing our fit. Why was it skewing our fit? What about the whole setup causes a data point that's far away to skew the fit? You can say it louder. Squared error. Okay? We're using an L2 norm, and L2 norm says that somebody who's way off the line is going to pull the line harder than somebody who's just a little bit off the line because those errors get squared, so big errors get huge influence. So another possibility is to use a metric such that big errors don't get big weight. Now, the quadratic error for small errors is doing something we like. It's giving us closed form solutions. It has some nice behaviors that maybe we like. But for big errors, continuing that quadratic forever is a bit of a problem. So in statistics, there's a whole domain of how do I make my statistical procedures for all sorts of things that I want to do robust to breakdowns of various kinds. Robust so that big errors don't get undue influence. Because the influence of an error is going up like this, right? So the bigger the error is, this guy is all of a sudden contributing a huge amount to the total error, and so reducing this one guy matters a lot. compared to all the guys down here. Even though there's 1,000 guys down here, this guy over here is getting way more influence. In fact, in robust statistics, one literally talks about the influence of a data point, meaning small changes of that data point are changing your estimate by a lot, whereas small changes of a data point down here are changing your estimate not at all. So this guy gets a lot more influence. It's kind of like the derivative of the estimate with respect to the data point is a way to think about it, if that helps you. In any case, so if you use the blue curve as your error function, then big data points are going to get extra influence. So a way to potentially fix that is to stick with the blue curve initially, but then go below it. Now what have I done with this new error metric, the red curve, that's a big no-no and it's going to make life complicated? What is it going on with that red curve that is not true of the blue curve and that I've already told you will make life miserable?
Convex.
It's not convex.
Yeah.
Right. If I take this part of the red curve and this part of the red curve and connect them, I go below the curve, not above the curve. Which is to say that the error landscape might have local minima. And certainly all of our techniques right now don't exactly work. And I just realized that I don't think it's on a slide. Oh, maybe it is. Okay. So, I mean, there's no closed form solution to minimize the errors where errors are measured with the red curve. Like there was for the quadratic. You can't just write it down and say, okay, here's what you do. So there's an algorithm, not guaranteed to work, but usually does, that uses two things that we've talked about already. One is least squares, which we know how to solve, and one is weighted least squares, which we know how to solve. So suppose I do least squares with this curve one time, with all my data. And suppose I now take the data points which have big error, and the error was computed like this squared, but I wanted it to be computed by the red curve, which means that data point got the ratio between these two curves too much weight. And suppose I now decide on the next go round I'm going to fit him again, except I'm going to give this guy a weight that reduces his influence by this much, and then do it again. That's the general idea. It's called iteratively reweighted least squares. So we're doing least squares, we're doing this quadratic fit that we have a closed form answer to, except that each time we look at the errors and reweight the data points that have undue influence to give them less influence. So that's the big hand-wavy version of it. So how are we going to do this? So we want to do weighted least squares regression. So we're going to do regression, but give each data point a weight. But the question is, where do we get the weight from? So what we're going to do is say, I wanted to what? That's not true. Arrow.
What?
What is their derivative here? That just seems wrong. And I've never noticed the prime there before. Okay, think about it for a second. And meanwhile, I'll go, this guy has way too much influence, this big error. And we'd like the influence to be this. So we're going to reweight it by the ratio between those two, which is exactly what's written here, except if you ignore this prime, which is bugging me because the derivative makes no sense. So unless you tell me I'm like, have forgotten how this works, that prime just looks like it's out of place. Not sure why it's there. So now this guy gets a weight, and we do a weighted least squares regression. So the guy that had undue influence now has his influence reduced to what the red curve wanted it to be. We fit again. We're going to get a new set of errors, some of which are going to be close to what the red curve would have implied, even though we're using squared error, some of which will be too big. And so we'll continue reweighting until the thing converges. And so what you find is the betas will start out with, for example, in the 1D case, with a huge influence of the outlier, And then as we reweight, it's going to slowly relax down to the right answer. The right answer as determined by this curve rather than that curve, even though we're using that curve and weights to simulate the red curve.
So we're adjusting the weights only on the outliers, but again,
You're going to do it on everybody.
Okay. Well, how is this different from
Well, you don't know what's
swaying down all of
well, so you don't know how much weight you're from the get-go. You don't know how much weight everybody should get, right? So you did this fit, and this guy was way off the fit, and so he should have gotten a new weight. But then when you use those new weights, you're going to get a new fit, and his error is going to be different than what it was last time. So the weight he deserves now has changed, along with everybody else. So basically, everybody gets a weight based on this formula. Then you fit again, and everybody's errors change. So everybody gets a new weight based on this formula. And then you fit again, and you iterate until it asymptotes, until basically the betas stop changing enough to bother redoing the process. So it's not guaranteed to give you exactly what this would have gotten, but in many cases it's quite well behaved. Okay? Yeah?
Should there be a square in the denominator?
No, because you're taking, weights were always positive numbers. And weights were always, wait, why do you want to square the weight? It's going here, and giving somebody a weight which is meant to change his influence proportionally so that I drag this down to here. So I'm multiplying by this over this in order to take the error and come back down.
Yeah.
But that may be the issue about the prime, which is now
I mean,
tripping over.
the denominator should be d squared. As I understand it, it should be fd over d squared.
That sounds awfully right.
Or maybe that's why they're prime.
That's just so strange. Why have I not noticed that as I prep this year and last? Don't remember. I'm going to go back and think about that and tell you next time to clear up the cloud that we've just raised. Because that's bugging me. Oh well. Leave myself a note. Yeah, question?
So when we iterate, just to try to get the best fit, is that when we run into issues of like, maybe now we're starting to also fit the noise of our data?
No, we're not increasing dimensionality at all here. All we're doing is determining which points are outliers by how much and reweighting them so that we're effectively using robust weighting, robust error metric rather than this non-robust subject to outliers error metric. There's no change in dimensionality here at all, and we're using the closed form inverse, just pseudo-inverse every single time, just the same way. So the dimensionality you've picked in advance for this problem, we haven't, we're not doing, if you want to mix polynomial regression with this, you'll still have the issue of polynomial regression. As you add regressors, you're going to fit more and more of the noise. But it's orthogonal to the question of weighting and robustness. Okay. All right. I've gotten way past where I meant to get to today, so we're going to start a new topic, unless there's more questions. Now, I deleted the wonderful drawing with all those ellipses and paraboloids and elliptical paraboloids we started with. But now we're going to come to why you wanted to know that in the first place. So suppose I not only want to fit my data well, but suppose the betas aren't allowed to be just anything. Suppose the betas are going to be constrained because you're telling me the betas can only be thus and so. So there are problems where this comes up, and I'm going to give you an example in just a second, just to motivate why you might want to do this. But the two that come up most often are you're allowed to pick any betas, but they have to satisfy a linear constraint. So this dot product has to be a constant, it can't be anything. So the betas have to lie on a line, effectively, or a hyperplane. And the other one is where the betas can't be arbitrarily big. So, for example, the length of the beta vector needs to be a constant is one example of that. So, first let's motivate why you might ever want to do this. So suppose we're in a multivariate case, we've got a bunch of y's, we've got a bunch of x predictors. So here's my y n, there's my y vector, and suppose I've got some x1, xn1, that's the first regressor, and x12, xn2, and second regressor, here's the third regressor, x1, x13, x23, xn3. Okay, so here's one of these standard regression things. I want this to be fit as well as I could by a weighted sum of those. But suppose I'm going to switch from beta to w for a second for a reason that I will explain in a second. So suppose my concept is that the y's are accounted for not just by any old combination of these, but I think this is my theory, for whatever reason, that I think the y's are weighted averages. Okay? Suppose I have some situation in which I think somebody's doing a weighted average, but I don't know what weights they're using. In other words, suppose I think that W1 plus W2 plus W3 equals 1. That's a weighted average. Okay? So that means that I'm doing multivariate regression, except that my betas can't just be just anything. The betas have to satisfy this equation. Okay? So this equation is a linear constraint. It's W dotted with the vector 1, 1, 1 equals 1. Otherwise known as this. Okay? So this is beta. I was calling it W because I wanted to say weighted average, but that's beta. So C is 1, 1, 1, and alpha is 1. Okay? So it's not the only example where this came up, but just to give you a feel for why would you ever want to do this, because you may have a theory about what the betas are doing. And one example is that the betas want to add up to 1. Now there's some other subtleties about this that would take it outside the realm of constrained least squares of regression, and one way in which this leaves that domain and makes the problem much more complicated is that you probably, if you say weighted average, don't just mean this. You mean something else. You also mean that Wi is greater than or equal to 0. Normally when you mean weighted average, you don't include negative weights. That's a much more complicated problem, which we can still handle, but it has some extra aspects to it that make it much more complicated than what I'm going to talk about in terms of constrained least squares of regression. So we're just going to stick with the case where there's one linear constraint and say, where does that take us? Okay. So let's talk about how you solve this. And to do that, we're going to go right back to those, that fancy paraboloid again. Okay? So let's take the board away. I knew that was going to happen today. You just had to. It's a rule. Once a week, for sure. Okay. Okay. So, going back to our y's and y stars and betas and beta stars and all of that. So we started out with y and beta, and we did these transformations that involved, let me rewrite them and make sure I write the transposes in all the right places before I screw up. Where is that? Where is that? There we go. and stretch. S. Now we're in Y star and beta double star. Okay, so this is where I started today in the review from last time. Now, let's do this in 2 dimensions. So here's beta 1, and here's beta 2. And we're looking for beta opt. Except now we get a constraint. So C dot beta has got to equal alpha. What does that mean? So let me draw C. C is just a vector. It's got the same number of components as beta, so therefore I can draw it in this space. So suppose this is C. Okay, what's C dot beta? How's it computed? Let's start for the moment replacing C by use of C, a unit vector in the direction of C, which will make it easier to understand where I'm headed. So suppose I have a unit vector in the direction of C, and I take beta dot UC. What number is that? Dot products, the definition from like the very first week. What's a dot product with a unit vector give you? There's a given beta. What do I do? Projection. Okay, so here's beta onto C. So this length here is beta dot UC. And suppose I want beta dot UC to be a constant number, alpha prime. So then I pick an alpha prime, let's say that is out to here, and what's the set of betas such that the projection is alpha prime? It's all the betas that lie on this line. Okay, so that's for UC. For C, I got to take the fact that C has already got a length, maybe not 1, so I have to fix that, divide by it. But regardless, the locus of betas I'm allowing myself to use is a line perpendicular to C and perpendicular to UC at a particular place along the C line. Okay, that's the constraint. Okay. Now, somewhere in this diagram is beta opt from linear least squares regression that we already know how to solve. Suppose it's here. Suppose that's beta opt, unconstrained. Right? Now, what do we know about how much the error goes up? Remember, we're still trying to minimize error here, but we're not allowing this beta opt to be used because it's not on this line. Okay? So we're going to go away from beta opt and error is going to grow. How does error grow away from beta opt? What's it look like? So suppose I'm going to let error go up by just 1. What does the locus of betas with an error of 1 look like? What shape does it have? As plotted by me at the very beginning of today and also at the end of last time. What's that?
Circle?
Not in this space. In that space. This space, it's an. And is it aligned with the coordinate axes necessarily? No. So errors look like, let's say, that. And bigger errors look like that. And bigger errors still look like that. So where is beta opt constrained going to be? Geometrically, I don't know how to make this happen yet, but where's it going to be? What do I want to have happen as I keep drawing these bigger ellipses? You want to touch the line. And you want to just barely touch the line. Because this one just barely kisses the line, and any other one has bigger error and goes through the line and in fact hits the line in 2 different places. So I want to keep increasing the ellipse until it just barely touches, and that's going to be beta opt constrained. Okay, that's the problem we're trying to solve right now. Okay, so geometrically it's clear, but this is some arbitrary straight line, and this is ellipses that are not even aligned with the coordinate axes, and that just sounds complicated. But in order to make it not only not complicated, but obvious, I'm going to head over to this new space. Okay? So let's think about what it means to head over to this new space. So let's get back to where I want to lines here, that I have a family of ellipses that I can make as big as I want, and each time I make them bigger, error is getting bigger. And so if I just keep expanding this ellipse, at some point it's going to just barely touch the line.
Oh, so it's not in 3D, it's actually
This,
also projected.
this is 2D. This is the beta plane. Yeah, well, did I draw the... Oh, look at that. I drew the axis as if I was doing 3D. Beta 2. The error is coming up, but I'm not even showing that. I'm just showing in beta 1, beta 2. Yeah, I started out drawing a 3D drawing and didn't actually mean it. Okay, so that's what we want to solve. So now let's go over to beta star. So beta star said that I'm going to rotate the betas by V transpose. In other words, beta star equals V transpose beta. Right? That's what happens when we go to this new space over here. And that's going to rotate the axes. It's going to rotate the ellipses. It's going to rotate UC. Everything's going to rotate. Okay? So in this space, we have beta 1 star and beta 2 star, beta 2 star, and the ellipses are going to rotate somewhere else, and they're now going to be aligned with the coordinate axes. So let's imagine that it rotated over here so that the new beta opt is down here, and my ellipses are now like this, nicely aligned with the coordinate axes. And UC is going to rotate to some other direction. Maybe it points down this way. And maybe the constraint line is going to have the same length, so we'll take this length and put it over here. So the constraint line is going to be here. And so I'm going to take these ellipses that are now aligned with the coordinate axes and then try to hit until I just kiss this line. So it's exactly the same as this picture, just rotated by V transpose. Everything in the picture rotates together. Okay? It still doesn't look all that easy to solve because I'm trying to figure out how big does an ellipse have to be until it just touches a line that is, not through the origin and, tipped and all kinds of stuff. All right? So now we're going to do this transform, which will finally make the problem easy. Just as it made solving least squares regression easy in the first place, it's going to make solving constrained least squares regression easy. So now we're going to stretch by S. So we're going to squish, we're going to stretch. The constant error surfaces are now going to become circles. All that's going to happen. But C is going to have funny stuff happen to it too by the same transform. Okay? So now we're going to come over here. We're going to have beta 1 double star, beta 2 double star. So we're going to squish, we're going to stretch. We're going to have a beta opt double star somewhere. We're going to have nice little circles around it. And finally, C, of course, is also going to get changed, right? Because it's going to squeeze in a little bit this way, but squeeze up a little bit that way. So C is going to point somewhere else. So I've been giving these vectors names. Here we had UC, so this is going to be UC star. This is going to be, it may not be a unit vector anymore because we've squeezed it and stretched. So, actually let's not use U for now. Let's use the actual C's. So we'll have C here, and we'll have C star here, which is still the same length as C because it's just a rotation. And now we're going to have C double star, which won't have the same length anymore because we squeezed and stretched, but it'll be another vector, and there'll be some distance along this vector where there is this perpendicular. Okay. So this is all pictures. Eventually I'm going to write the equation so you can actually solve it, but the picture part is the clue to solving it. Right here in the middle of the circles is beta opt in this double star space. Around it are circles. They're getting bigger and bigger. So what? Yeah.
This might go back a bit, but
No, please.
I'm not totally I'm not. Can you go back over what those circles exactly represent? I know they represent errors, but I don't see.
They represent
the circles.
iso error contours,
Okay.
meaning a along this ellipse, the errors are all the same. Along this ellipse, the errors are all the same, but bigger than the smaller ellipse. When the ellipse has size 0, meaning it's a dot, that's minimum error, because there's the optimal. So as we go away from it, the error is growing. But this is saying, for a fixed amount of error, what's the shape of the circles that all have equivalent errors?
Like any point in the ellipse is actually representing a vector going from the origin.
This is just a different beta I could have used.
Okay, yeah, I'm just saying like the beta is a vector, right?
Well, here's beta 1, beta 2. Beta in this case is a dot. This is a different choice of beta that's worse. This is another choice of beta that's worse in the same amount.
But the beta has an x coordinate and a y coordinate.
Correct.
So it's actually a vector going from the origin to that point.
Okay.
Like-
There's a beta, there's another beta.
Okay,
Sure. That's true.
I just wanted to make sure.
That's true. Okay, so these are ISO error contours, and we want to minimize errors. We want the smallest ellipse that satisfies the constraints, which is just kiss it. When we rotate, we want the smallest ellipse that just kisses it. Now it's kissing it down here, but it's the same idea. Now we want the smallest circle that just kisses this line. So now let's look at this. We have C, which is a vector, which defines the line. We have a beta star star opt, which defines where we'd like to be, except that's not on the constraint line. So where on the constraint line, so first of all, going away from here in any direction is bad. So we want to go as little distance away from beta star star opt as we can get away with. But we have to be on this line. This is a problem we've heard of before. I have a point, I have to leave that point. I have to meet this line, but I want to meet it as close as possible. So the line, the vector from beta opt star star towards the answer to our problem is going to hit this constraint line at what angle? Perpendicular. Means I'm going to have to do that, and this will be the answer. This vector here that I just did, and this vector here, otherwise known as C double star star, what is true about those two vectors? They're parallel, which is to say the answer is going to be beta opt star star plus some amount. I need to call, what letter do I usually use for that? Where do I do that? I just want to keep consistent with my notation. Oh, gamma. Plus some amount of C star star. The answer is going to have that form, and we're going to solve for the gamma that puts you on this line. I want to take the optimal solution, I want to head in the same direction as C and keep going and going and going until I hit the line. So I'm going to just say, I want something that looks like this, but that is also on this line. Which I can do because I know the definition of this line. Definition of this line is you do a dot product and it has a particular value. So I'll do the dot product, set it to the particular value, and solve for gamma. So that's the broad strokes without actually doing all the symbol pushing. The geometry is, I want to leave beta opt and pick a beta such that the error is minimal, which means the ellipses will just barely touch this line. Then I'm going to rotate, so now the ellipses are parallel to the coordinate axes, but I still have to go out in this new direction, go out from beta opt in some direction until I just barely touch this line. But that's still completely obvious, unobvious, because it's ellipses in some arbitrary line. So instead, I do the third transformation, all of which you've seen before, because it's how I solved least squares regression in the first place. Now they're circles, and now I know which direction to go. It's the same direction as C. C double star. Okay, and I just go that direction until I hit the line, and that's your answer. Okay, so now what we have to do is go back and say, how do you do all of this? So, this rotation from here to here was rotate by V transpose. I'm only caring about what happens to the betas, not what happens to the y's, which we're not worrying about. So, this was just rotate by V transpose. That's how we got the beta star space. We rotated this, which means we also rotated C. So C star is equal to V transpose C. That's halfway. Then the next step to get from beta star star from beta star to beta star star was basically to multiply by s. Now it was complicated. It was way back when we did all this stuff. S had the same shape as the data. It was this huge matrix that had, you know, S1, S2, and everything else was zeros. But when we absorbed S into beta, all this stuff was irrelevant. And we just multiplied the first beta by S1 and the second beta by S2. Okay? So effectively, we're multiplying by a slightly different matrix that, you know, I'm just going to give a name to. So we're going to call this new matrix S star, and that's this matrix, S1, S2, 0, 0. Okay? So let's just take the top bit of S, throw out all the zeros in the bottom, and make myself a nice little square matrix. And then that means that this arrow is beta star star equals S star times beta star. Right? That's the stretch the axes. Which means what it does to C star is the same thing. C star star equals S star times C star. Now, there's a little bit more subtlety. Because we don't just need to know C star, we have to know what happened to the constraint line. Okay? So, what was the constraint line before? The constraint line when we started was the locus of points where, in that order, where C dot beta equals alpha. That was the constraint that defined this line. Right? Now, we rotated the space, but we didn't reshape it here. Right? C star has the same length as C had. And the line is rotating along with it. So over here, the constraint is C star dot beta star equals alpha. That's the constraint over here. Right? We rotated C star, we rotated beta star, their dot product didn't change from C dot beta. Okay? Question is, what happens over here? Because now we're doing something that's not a rotation, we're doing stretches. So things are changing. Everything's changing. So, let me not trip on myself here, get that right. Where is that written down so I don't do it wrong? Okay, so let's work out what the constraint is over here. I've run out of board. Not being sure where to write this. So, the constraint is C dot beta equals alpha. We know that. And so I want to write C star star and all this other stuff over here back in this world so that I write the constraint. So C star star is S star C star, which means that if I want to go backwards, C star is S star inverse C double star. Right? This little silly matrix, this one is invertible. It's just 1 over S1, 1 over S2. So where you used to stretch, now you squeeze. Where you used to squeeze, you now stretch. Okay, so if I want to get back from anything in star space and get back to this middle space, I have to unsqueeze the axes, which is all this equation says. Okay? And this equation, sorry, where is it? This equation also is invertible. It says that if I want to get back to C, I got to multiply by V. V transpose inverse is V, which means that C is V S star inverse of C star star. That's just going back this way. Okay? I have a C star, it's in this space. I want to go back one step, I gotta unstretch and unsqueeze the axes, which is what this will do. And then if I want to get back to here, I have to unrotate in the opposite direction that I rotated before. Now, we know that C dot, oh, and the same is true for beta. Let's see, do I need that right now? No. So we know that C dot beta is supposed to equal alpha. We know that C can be rewritten this way. V S star inverse C double star dot beta. Now, do I need to write out beta double star? Yes, I do, I think. Yeah, I want it to be those terms. So I want to dot product that with what beta is, beta is, and beta, yeah, let's just do that. So beta double star is this times beta star, which is this, so I can do the same thing backwards. So I'm going to substitute for beta V S star inverse beta double star. So I know all that has to equal alpha. That's just rewriting the equation we already knew. This is C, this is beta. But now inside there are the new vectors in the space that we're currently living in here. And I want to figure out what this line is. Right? Now, this vector has a V in it, so it's rotated from this vector. This vector has a V in it, so it's rotated from this vector, which means that this dot product won't change if I multiply both vectors by V transpose, which means I can delete these two guys. But now I've got what's happening to the dot product as I rotate, which is to say, so what's a dot product? So I've got this guy dotted with that, except I'm stretching the two axes. So I can compute what the dot product would be in beta star star and fix it. Okay? So in other words, I can figure out what's the new value of alpha, so I'll call it alpha prime. The constraint here is going to be that beta 1 star star dotted with, no, I'm sorry, that's just false. That's just false. Okay, getting myself finished again. Damn it. 1 second. While I unconfuse myself. Crazy. There is a dot product whose name I'm not going to write for you right this second because my notes just look completely wrong, such that that's our constraint. And it's with C star star, but I don't know why this just looks wrong because of the stretching. Regardless, when you're all done with this, you have to decide, take beta opt and add just enough of it to be on the constraint line. What does that mean you have to do? It means you have to do, I don't want to erase any of this, but we're not filming the other board, so move the camera please, because I cannot erase any of that. We want, as I wrote down there, to add to beta star star opt. We want to add some amount of C double star such that, so this is going to be beta star star opt constrained. So we're going to move in the direction of C double star, as I said. We're going to start here and we'll go in this direction until we hit the line. So what does hitting the line mean? Hitting the line means such that beta star star opt dotted with C double star, this is the part that's been vexing me, is equal to, and my notes say that alpha goes here, but that just seems wrong. So this is the part I have to fix. But regardless, whatever constant needs to go here, we can now put this in. So that's constrained. Sorry. So beta. So now we're going to substitute for this formula. So that's beta star star opt plus gamma times C double star dotted with C double star wants to meet the constraint. We got distributive law, so we can take beta star star opt dot C dot C double star. And at this point we know what these are because we've already solved the unconstrained problem. I better not go too far to the right at this point because nobody can see the problem over here. So this is a constant. And this is plus gamma C double star dotted with itself, otherwise known as length squared. This is a number we already know. The only thing we don't know is gamma. We know alpha because it was given to us by the problem, and so we solve for gamma. Okay? So the logic is take this problem, this geometric problem, translate into a coordinate frame in which the solution is obvious. The direction you need to go from beta is obvious, and then just figure out how far to go to be on the line, which turns out to be just a linear equation that's easy to solve. Having done that, we now have our solution. We know where this is. So what we know is beta double star opt. Okay? But that's not what we wanted to know. What we wanted to know was beta opt constraint. So we take this guy, go back to here by unstretching the axes, by multiplying by S star inverse. And then we go back to here by rotating by V. V transpose went that way, V went this way. And so the answer in the end is beta star star opt constrained times S star inverse, that's the unstretch and unsqueeze, times V. Oh, sorry, no stars here. So you go follow this arrow, solve the problem, get the solution, take the solution back here, take the solution back here, done.
And MATLAB does it in like 3 lines, right?
Yes. Exactly. And so will you. And I'm going to stop here because A, I need to found the two problems that I left you with cloudy, which I'm really so sorry about. B, the next stage is to do the quadratic problem, which error will be